So before I get started with the lecture today, I just wanted to give you a quick reminder of where we're at. So here we are in the schedule. I just did a quick poll of the class to see how many people had actually downloaded and looked at the assignment, and it was probably around half of the people who show up, which means it's probably most of the people who don't show up. And 5 of your 12 days are already gone. So this is due a week from now, and it will probably take you a couple of days. So please don't think that you can open this on the last day and finish it, especially if you're a grad student, because that IDDFS is a little bit tricky. So if you're watching this and you haven't downloaded it yet, please get on that. It's not a trivial assignment, especially since it's the first one and you have to sort of, figure out how everything works together. So please download that. Another announcement is that so the Discord link that I sent out for the class Discord server, that expired. Those links are only good for a week. And so after class, when I get back to my office, I'll post a new link to the Discord server. So please join the Discord if you're not if you're not a Discord hater. Like it's great. It's really easy to answer questions. I've already answered about a dozen questions so far on Discord. The only thing is, if your question is like generally applicable, like for example, I didn't quite understand this, post it in the general channel so I can answer it for everybody. But if it's like, hey, why did I get this grade on the assignment, which is like personal information, then you can DM me. So try and ask general class questions in public so then I can answer it, because I'm sure if you had the question, then probably 20 other people had the question as well, and it's really easy to answer it there. All right, so make sure you get started on that, because if there's any excuses on the day that it's due, that's my only rule, right? Like, don't wait until the day that it's due to ask for questions. All right, so let's get started. So today I'm going to be talking about heuristic search or informed search, and especially the A-star search algorithm. The A-star search algorithm has like so many uses. It is in possibly every video game that you've ever played that involves things moving around. So it's a very important algorithm. And it is very, very widely used, and there are lots of different variants of it, etc. And it is what Assignment 2 is all about. So here, this is a link to a search demo that I have on my website. I'll be giving a demo of that to illustrate some of the things we've learned during this lecture at the end of this lecture. But I just wanted to include the link at the beginning so you don't have to scroll through, there's a lot of slides in this particular lecture because I have an illustrated example, and there's a lot of different slides for that, so I just put the link at the beginning and it's at the end as well. So informed search. So far we've been talking about uninformed search, but now we'll talk about actually using some knowledge of our environment to help us with this process of searching. So an informed search strategy uses problem-specific knowledge beyond just the problem description itself. So just a quick example of that is, again, this example of me trying to navigate in this room. As a human, you are using guesses all the time, right? So if the door is over there, I should probably start going in that direction, right? Now in this case, it's actually interesting because the quickest path to the door is not me moving that way first because there's a desk in the way. But me as a human, I still recognize, okay, I'll probably have to go that way at some point. But if there was a maze, then that knowledge may actually guide me in the wrong direction, right? So typically it will help me, but there are some times when it may not help me. So heuristic search uses guesses or heuristics to guide the search toward the direction of the goal. And just a quick note is that every branch of science has its own definition of the word heuristic. But what we are using it for in this course is a sort of evaluation function. It is a heuristic evaluation to say, okay, it's some sort of knowledge that will help me find the goal faster. So that's what the definition of heuristic is in this course, but you're going to find, at your job, at your home, there's so many definitions of heuristic, but that's what it is for this course. And ideally, what this is going to do is it's going to reduce the total number of nodes searched in your search algorithm, and typically it does. And hopefully, by reducing the total number of nodes searched, you are also going to speed up the amount of time, or lower the amount of time necessary to complete the search. And you might say, well, if we reduce the total of nodes searched, of course we're going to speed up the search, but it may be the case that the heuristic evaluation function we're using takes so long to compute that even if it does reduce the total number of nodes searched, that the actual search time is going to be higher. So there's always these trade-offs in computer science, right? So the speed at which you can calculate the heuristic function that actually helps us is a factor as well. So let's just look back at breadth-first search as a quick recap. So we start over here at this node. It is the node in the open list, and then we saw that breadth-first search does a literal breadth-first search. So every node at subsequent depths are expanded before anything at lower depths. And so what we see is this kind of blind or uninformed search. It has no idea where it wants to go. It'll just find the goal at some point and we'll say, okay, this is the path. So this is breadth-first search. But there's another algorithm or a class of algorithms that we're going to be talking about, and A star is a subset of this algorithm, or it's a type of this algorithm, and that algorithm family is called best first search. And of course, this is also BeFS, right? So we're overloading the BeFS, so I'm going to call this BeFS for best first search. And it's an instance of general tree search, so it's the same algorithm that we've been looking at this whole time. But what we're going to do in this algorithm is we're going to come up with some function. That function we're going to call f of n. So it's a function on a node n, and we are going to select a node from the open list to expand based on that function. And so typically, we are going to select the node with the minimum value of f of n, and that's going to be some sort of guess, some sort of heuristic evaluation of how far I have left to the goal. And so best first is a little bit misleading, right? We don't actually know which direction is best, because if we did know which node we should expand first to get the optimal path, then there would be no process of search, right? If we knew the best one, then we would just go there, and it would be just a straight path. Search wouldn't even be necessary. And so this algorithm is sort of like a best guessed first, right? Rather than actual best first. So BeFS, or best first search, can be implemented with a general tree search by using a priority queue for the open list sorted on f of n. So if you think about it, you can just use an array for the open list if you want to. But if we're trying to get the minimum value of f of n, if we just use an array, and that array is just, okay, whatever order we happen to put things in, then in the worst case, we're going to have to search every possible node in the open list to find the one with the minimum value. But there are some data structures, namely priority queues, heaps, etc., that keep that open list in a certain way so that we can always get the minimum value or the maximum value, if we want to, in constant time. Okay, so we'll be using a priority queue for that in this course. And there are so many different priority queues. I'm actually going to give you one implemented in JavaScript for assignment 2, so you can use that if you want, or you can just use the array if you want. But using a priority queue that can get you this node from the open list very quickly is going to speed up your search dramatically. There are a whole family of best first search algorithms. They have different evaluation functions, but they do have this heuristic function h of n. So h for heuristic, really easy to remember. That h of n is going to be our guess at how far we have left to go, for example. So h of n in our course is going to be an estimated cost of the optimal path from any given node n to a goal node. Okay, so we're going to take the state of this node and we're going to guess how far I have left to go. So example of this room, I would guess that the window has a lower value of h of n, the estimated cost of going there. I'm going to say I have about 4 meters to that window, but I might have 6 meters to that door, right? So it's not exact, it's just going to be a guess at how far we have left to go. Heuristic functions are usually the most common way that we incorporate additional knowledge into our search algorithm. And just a quick definition, if n is the goal node, meaning that this is a node that satisfies our goal condition, then h of n is equal to 0. So we just define that. If we are at the goal, then we are defining that our heuristic function is 0, because I have no distance left to go. There is no cost to get to the goal if I'm already at the goal. And if we somehow knew the perfect heuristic, so a perfect guess at how far we have left to go to the goal would be the optimal path cost. So if we were some oracle or deity that knew the exact guess, then this is h star of n. So wherever you see me reference h star of n, that is essentially the perfect guess, which would be the optimal cost to the goal. So, okay, we've talked about heuristic functions. Let's have a look at them. Here are some examples of heuristic functions. First, let's say that I'm up here. This is my start, or this is the current node that I'm at, and this is the goal down here. What is an example of a heuristic function? Can anyone put up their hand and just give me any function that could estimate the distance from a current node to the goal node? There's no wrong answer here because, yep.
15.
No, a function. Yeah. Yep.
A function that would give the direction.
But we're trying to get a number, as in like the guess of the distance. Yep.
The Euclidean distance between the two points.
Sure. There we go. That's one function, right? You take where you are, you take where you want to be, you draw a line between them, and you just get the distance, right? So here, I'm not going to make a guess at what that, maybe it is 15, whoever said 15, right? So, but we are essentially taking in some input x and y and some goal x and y, and we're producing some value of distance. Okay, now just keep in mind that for this course, we're essentially just going to be working in these grid worlds where we can move up and down, left and right on these grids. But all of this also applies to arbitrary graphs as well. Okay, so you can think about a grid as a special case of a graph where each state is a node in the graph and the edges just connect to the neighbors. All right, so even though I'm only going to show examples from these grids, which I think are a little bit more intuitive, all of this can be applied to nodes as well. Here's another example of a heuristic function where we're going to say, okay, well, maybe if I can only move up, down, left, and right in my environment, maybe a more accurate guess at how far I have left to go to the goal would be actually taking the distance in up, down, left, and right, right? So I take maybe the difference in the x and add it to the difference in the y, and now I have another heuristic function. And here, in this example, you can see, okay, this one might be a little more accurate because the Euclidean distance passed right through this obstacle that we would have to go around, whereas this one did not pass through an obstacle. But of course, this one could pass through an obstacle, right, depending on the environment. So if I have this situation where I'm trying to get from here over to here, then it's never perfect, right? What we're doing here is we're making some sort of guess at how far we have left to go, but that guess may vary wildly in its accuracy depending on how convoluted the map is or the environment is. So that's just some examples. I'll get back to those in a little bit. So greedy best first search. Yep, we had a question?
For the heuristic function, isn't that going to be just another form of search?
Nope, because so this is just a guess. So the question was, is the heuristic function just another form of search? No, because we're taking the xy of where we are and the xy of where we want to be, and we're just finding the distance between them. So there's no searching. There's no trying of actions. There's no anything. We're just saying, I think I'm going to be this far from the goal. It's whatever function, but it just doesn't do any search, right? We don't want to do search within search sort of thing. Okay. So of the best first search algorithms, the most intuitive one is this one called greedy best first search. So greedy usually means really fast. We'll see if that's the case. So greedy best first search is going to look at the open list, and it's going to expand the node on the open list that it thinks is closest to the goal node. Couldn't be simpler, right? So hopefully this will lead us to the goal faster. And so for greedy best first search, remember we said that for best first search, we have some f of n that we're trying to minimize. And so for greedy best first search, f of n is just equal to h of n. And if you think about it, if I evaluate all the nodes that are around me, so for example, let's say I'm back here and I'm trying to get to that door. Well, the one in front of me is probably going to have a lower value of h of n than the others because I'm just physically closer to it. Right? We're not taking any obstacles into account or anything. So with greedy best first search, I would probably choose to move forward first in order to get to that door. And so in practice, this is going to, if you look at the search, it's going to resemble depth-first search because it's greedy, right? It's trying to get all the way to the goal, and if it runs into any issues with obstacles, it's going to back up and then try another path and back up and then try another path. And so this is greedy best first search. It's the same algorithm that we've been looking at, just slightly modified. And so wherever you see PQ here, that's just me shortening priority queue, because if I typed in priority queue, it would just take up too much in the slide. So this is the exact same algorithm as our general uninformed tree search. However, now we are sorting this priority queue based on F, which is equal to H. So it's just taking the minimum value of F. So whenever we get a node from the open list, we are popping the minimum value of F from the open list. That's it. Same algorithm. We're just changing how we take something off of that open list. Let's look at another example. All right, here's how greedy best first search can help us in general. So let's say we're over here and we want to get over here. If we were using breadth first search, this is what would happen. We would expand depth 1, depth 2, depth 3, depth 4, all the way up to the goal node. And so you can see here, we have expanded pretty much everything in this environment because it's this sort of growing radius. And if you're all the way over on one side and the goal is all the way over on the other side, then you're pretty much going to fill up the whole map and expand absolutely everything. So ideally, what we would want is some sort of guess that would guide us toward the goal a bit faster without having to expand absolutely everything. So let's look at greedy best first search. And let's take Euclidean distance as our h of n, right? So what we're going to do is, well, okay, right now at the start, we only have the root node in the open list. So let's expand the open list. And by the way, we're working with diagonals now as well. We're not just going up, down, left, and right. So what we do is, we now have these 8 nodes in the open list. So we're going to take the one that we think is closest to the goal. And so we would just apply the distance formula to all of these nodes. And maybe we think, okay, this one here is physically closest to the goal. So that's the one that we're going to take and expand next. So we look over all of these, we look at their h of n, and we take this one. So now I expand that one and I generate its children and put those on the open list. Then the same process. I look at all the things I have in the open list and take the one that's closest to the goal. So I do that again, I expand it, and I do this process over and over and over, and eventually, it's going to take me here, then here. Oh, look, but now I can't go here, right? So I'm going to have to go up and then down, etc. But at the end, what I get is something like this. The heuristic has helped us dramatically in how many nodes we had to expand or visit on this search, right? So as long as that heuristic function isn't super slow, right? So maybe we expanded 1/10 of the nodes of breadth first search, but as long as that heuristic function doesn't slow us down by a factor of 10, then this search will take longer in terms of seconds to do the search or whatever, or milliseconds to get to the goal. So that's good. But this was the case where we had this little opening up here, right? So you can see here that greedy best first search is really great when there aren't many obstacles in the way. It'll take us right toward the goal if there are no obstacles. But if there are obstacles, like this, for example, now we can see one of the drawbacks to this is that whenever there are these, I call them concave structures, like little caves that are physically closer to the goal, but you can't actually get out of the cave, right? These sort of nooks and crannies in the maze or whatever. So here's greedy best first search in this case where we would go up, and we think, okay, this one is closer to the goal, so we'll expand that. And what we get in the end is we actually have to search all of these before we finally make it down here, right? So greedy best first search is great when it never has to back up. But it will have to back up eventually if there are obstacles in the way, okay? Now, the performance of greedy best first search, what is that? So it suffers similarly to depth first search because it is sort of going down before it explores outwards or backwards. So it's incomplete in general. If we are not, now here I have used a closed list in this example, but in general it does not use a closed list. So it may not find a goal, and it may get lost in certain paths if the heuristic is bad. It is not optimal because it may find a higher cost path than the optimal path. So those aren't great. And the time complexity is O of B to the M. So this is the same. It has the same theoretical properties as depth first search. Now in practice, if we use a closed list on top of this, this is the tree search version of it, it will usually do better than depth first search. But theoretically, in the worst case, it has the same time complexity. Now I'm going to talk about this concept of an admissible heuristic. So an admissible heuristic is a heuristic guess at how far we have left that never overestimates the distance to the goal. So it's always less than or equal to the distance to the goal. And you can see these as sort of optimistic guesses, because if it's always lesser than or equal to, then it means I think I have less to go than there is, so it's optimistic rather than pessimistic. And so another definition of an admissible heuristic is that h of n for an admissible heuristic is always less than or equal to h star of n, which would be the actual true optimal distance to the goal, or the perfect guess. And so if you think about this, g of n, we talked about g of n before, that's how far we've gone so far in our search, right? So if you take f of n equal to g of n, which is how far we've gone, plus h of n, which never overestimates, then this function of f of n never overestimates the true cost of a path through n when h of n is admissible. Okay, so just take a minute to think about that later. But that is a fact. If we take the actual how far we've gone so far, and then we have a guess that never overestimates, then we are never, that f of n is never overestimating the true total path cost through this node. Okay, so let's see if these heuristics that we just talked about are admissible or not. So, is the Euclidean distance admissible? Hand up if you want to answer in front.
Yeah, I mean, that would be the best path from one point to the other, so that would be the ideal, right?
Yeah, so I'm sure you've heard this before. The shortest path between 2 points is a straight line, right? If you are able to walk straight to something, that is the minimum possible distance. So if you are calculating the minimum possible distance, of course, that's going to be an admissible heuristic. How about h of n is equal to 0? Is that admissible? Yeah, because 0 is always going to be less than or equal to true path, right? So that's an admissible heuristic. What about, hand up if this is an admissible heuristic? Yep. What was your answer?
Yeah, it is admissible.
Why is it admissible?
Because if there are no obstacles in the way,
Yep.
and we're on a grid, that's the path we take.
So that's a fine answer, but the true answer, you have to mention, okay, what are the legal actions? Right? So you are absolutely correct if we can only move up, down, left, and right. So if our legal actions are up, down, left, and right, then this is like the Euclidean distance for up, down, left, and right, right? This is called the Manhattan distance. The reason it's called the Manhattan distance is because if you've ever looked at a map of Manhattan, it looks like this, right? There's city blocks and roads between them. So you sort of split up into this grid. So if you're talking about if I'm in Manhattan and I'm over here at this location and I want to get to like the bank or whatever, the Manhattan distance is much more accurate than the Euclidean distance because you can't walk through all the buildings, right? So this Manhattan distance is admissible if you can only move up, down, left, and right, but if we have diagonal movements or any other sort of arbitrary movements through this grid, then it may no longer be admissible, right? So you have to ask yourself, can this ever overestimate the distance to the goal? Well, that is going to depend on the legal actions. So next, what about the diagonal Manhattan distance, right? So is this an admissible heuristic function? Different person, hand up if you want to answer.
Yes.
So why is this one admissible?
This would be the most optimal path. It is the condition where hn is equal to h star n. And the last one wouldn't be because it was more than the most optimal, so it was overestimating.
So again, to be complete here, we need to mention that if our legal actions are only diagonals, then it would be optimal, right?
If it's anything, you can if you can move up, down, left, and right, and diagonals, even then I think it's admissible.
Yes, so it's admissible if our actions are the 8 around us. But just because we have a grid doesn't mean we can't move in arbitrary directions, right? So whenever you're answering this sort of question, you have to take into account what sort of actions are actually legal. And this, you said that this is equal to h star of n. It is not. It's only equal to h star of n if there are no obstacles, right? Because if there are obstacles, h star of n would be the optimal path cost that takes them into account. But yes, this is an admissible heuristic for octile movement in a grid. Okay, so those are examples of admissible heuristic functions, but if I ask you, well, not if, when I ask you on an exam, hey, is this an admissible heuristic function for a given legal action set, etc., that's what you have to take into account. Yes, question?
So would this be like not admissible for like a knight's move?
It depends on how that, like, you'd have to prove it, right? So you'd have to say, okay, what is the cost of that action? So you would have to show or prove that this is always less than or equal to any distance, right? So you just have to compare the actions, etc. But for our purposes, we're not going to be getting into complex movements like that. Yeah. Okay, now that we know about heuristic functions, we can talk about the A-star search algorithm, which is the best known or the most well-known or widely implemented best first search algorithm out there. Probably one of the most famous algorithms that I've heard of, at least. And so it's going to evaluate nodes in the open list by using g of n and h of n. So here the heuristic function is going to be f of n is equal to g of n plus h of n. And so f of n is an estimate of the cheapest solution via this node that we are currently evaluating. And so all we do to change the algorithm is we select the node from the open list with the minimum f of n, which is equal to g of n plus h of n. So the performance is going to depend on the properties of the heuristic function, but we'll get into that in a little bit after I show the algorithm. So here is A-star tree search. Exact same algorithm as greedy best first search, but in greedy best first search, we had f was equal to h only, but now we have f equal to g plus h. Okay, so we just pass that into our priority queue. The priority queue will keep that sorted, and we can just pop the minimum f off the priority queue. So this is it, right? Look at how easy it is to remember the A-star search algorithm now. I didn't have to list out the whole algorithm. You already knew the framework from the algorithm, right? From all the other algorithms we talked about. It's just how we select from the open list that's different. So this is A-star tree search. This is greedy best first search. And so A-star, we're going to figure out soon that A-star is an optimal search algorithm with the correct type of heuristic, because we are considering how far we've gone already on top of the heuristic, right? Greedy best first search doesn't care how far we've gone so far. It's just always concerned with getting to the goal. And so that's why this is not optimal, because it's only taking into account how far it thinks it has to go rather than how far I've already gone. So A-star search using tree search, meaning that there is no closed list, is complete. It will eventually search the entire tree. It will just search parts where the heuristic is lower first. Okay, so it is complete. A-star using tree search is optimal if the heuristic is admissible. Okay, so using a heuristic that is not admissible can and usually does produce non-optimal paths. So this is where the performance depends on the properties of the heuristic. Okay, so A-star using tree search is optimal if h of n is admissible. Okay, but we learned from the last lecture that using tree search, ideally we'd want to use this graph search with a closed list, right? Because we take all of these exponential time complexities and we turn them into the number of state time complexities. So A-star using graph search is what we really want to do. right? We always want to use graph search. We always want to use a closed list. So how does it perform using graph search? A star can return suboptimal solutions when you use an admissible heuristic using graph search. A star graph search using an admissible heuristic can discard optimal paths to a repeated state if it's not the first one that is generated during the search. So you may find a better path later on, but you don't end up considering it. And so we can fix this by imposing what's called a consistent heuristic. So, did you have a question? Yeah.
Just wanted to ask, is there any scenario in which the greedy best first search is preferred over A star search?
I'll get into that at the end of the lecture. Yeah. Okay. So when using a closed list, we can't just use an admissible heuristic. We have to impose an even stricter constraint, which is called a consistent heuristic. So a consistent heuristic, also called a monotone heuristic, this is a difficult concept to visualize, and it is a difficult concept to explain. So if you don't get this at first, don't worry about it. I'm not going to drill into proofs of consistency or anything like that on the exams. I just want you to know this rather than know it in complete mathematical detail. So a heuristic is consistent if you have, let's say we have two nodes, A and B, or two states for this example. If the difference in the heuristics is less than or equal to the cost of going between those nodes. Now, this is not intuitive at first. So h of n is the estimate path cost from n to the goal, and CAB is the cost of going from A to B. So in English, the change in the heuristic value between two states must be less than or equal to the actual cost to go between them. Okay, so let's have a look at that. This is an example of what's called a triangle inequality. Okay, so if we look at it like this as nodes on a graph, we have the heuristic or the guess between A and our goal, and the heuristic or the guess between B and our goal. And the difference between these two has to be less than or equal to the cost to travel between A and B. And if we look at triangle inequalities, it's essentially saying that Z, so if we take Z as the bottom line here in this triangle, the length of Z always has to be less than X plus Y in a triangle, right? And we can see as we flatten and flatten and flatten the triangle, X plus Y gets close to the length of Z, but it never gets exactly equal to it. So if I translate this into this, so I'm just going to move this graph so that it looks a little bit like what we just did, we can see here, for example, that h of A plus the cost to go from A to B is always going to be greater than h of B, which is just a rearrangement of this. Okay, so that's one way of looking at it. And another way of looking at it is not in terms of consistency, but an example of inconsistency. So if we are at node A in our graph, and our heuristic evaluation to the goal is, let's say, 9, for example. So I have 9 left to the goal. But then I go to B, which cost me 3, and now I think there's only 4 left to go to the goal. Then this breaks that triangle inequality. And this is why it's inconsistent. It is not, the logic here is not consistent. How can my heuristic go down by 5 when I've only moved 3? Right? So that makes it inconsistent. So digest that for a little bit. I'm not going to grill you on exams, but this is the property that we need to have in order for A star to produce optimal paths. So now we're going to look at the Manhattan distance. Is this consistent or not? It ends up that yes, this is a consistent heuristic if our values are up, down, left, and right, of course, or our actions. And so really what we're saying here, so here's the property of consistency. Here I have two nodes, A and B. They both happen to be the same state right now, but the heuristic, the difference in the heuristic between these two is 0, essentially. So consider two nodes that are right on top of each other, and when we move, let's say we move one of those nodes to up, down, left, or right, so the cost of going from A to B is going to go from 0 to 1. But the difference in the heuristic, because we're using this Manhattan distance, is going to change by at most 1. Right? So this is a really informal proof that if the cost is always 1, and we are sure because we're using this Manhattan distance heuristic that the difference in the heuristics change by at most 1, then of course our consistency is satisfied, right? Because the cost is changing by 1, but so is the heuristic, right? In the worst case, the heuristic gets worse, but in the best case, it gets better, so it goes down. So that's consistency in a nutshell. I'm not going to drill down too much into the mathematics of that. Every consistent heuristic is also admissible, but the reverse is not always the case, okay? So consistency, all consistent heuristics are admissible. So if we have this Venn diagram, consistent heuristics are a subset of admissible heuristics. In practice, it's actually kind of difficult to construct an admissible heuristic that is not consistent. Whenever I think of a heuristic function, like you basically think of Manhattan distance or Euclidean distance, etc., it's kind of tough to find an admissible heuristic that isn't always consistent. And so this is usually satisfied. And if h of n is consistent, this means that the values of f of n along any path are non-decreasing. Okay, so that means we are always choosing values of f of n in increasing order from the open list. And so the sequence of nodes expanded by A star using graph search is in non-decreasing order of f of n. Okay, so whenever we choose a new f of n, it will always be greater than or equal to the previous f of n that we chose. Therefore, the first goal node that we select from the open list with A star is going to be optimal, because all the later nodes that we would have chosen are going to be at least as expensive, and we have guaranteed that we've chosen everything from the open list that was less expensive. So if we've looked at everything that was less expensive than the optimal, then the first goal that we find is going to be optimal. Okay, so that's why consistency is required here. So A star using graph search, meaning it has a closed list, is optimal if h of n is a consistent heuristic. Okay? Now, if h of n is not consistent, but it is admissible, most of the time you will still get an optimal answer from A star, but it's not a guarantee, right? And we do want to guarantee these things when we're talking about our analysis. So here is A star using tree search, and so I've left out the part for the closed list here. So this is optimal if h of n is admissible, and if we introduce consistency, then we can say that A star is optimal with a closed list, so the graph search version. Do you have a question? Okay. So these are the two versions of that algorithm. Remember, the difference between tree search and graph search in the textbook is just that tree search has no closed list and graph search has a closed list. And so pretty much from here on out, if I mention an algorithm, we're going to be talking about the version with the closed list, because the version with the closed list is just better. You always want to use that if possible. Okay, so a quick recap of all the algorithms we've learned so far. Here is A star search. It has a priority queue sorted on f equals g plus h, and we're just popping the minimum value out of the open list. That's A star. Here is greedy best first search. All we've done is instead of f equals g plus h, now we have f equals h. Okay? Now, let's look at uniform cost search. Uniform cost search, if we rephrase it in this term, this value of n, well, uniform cost search said get the minimum g value. So if we just set f equal to g, that is uniform cost search, right? So uniform cost search only cares about how far we've gone so far. Greedy best first search doesn't care at all about how far we've gone so far. And A star is this nice middle ground where it cares about both. And so it can produce optimal paths. But look at this. Here's an example. How can I frame uniform cost search being optimal within the context of the A star search algorithm? Well, okay, f equals g plus h. What's h here? 0. Is 0 a consistent heuristic? Yes, right? So if 0 is a consistent heuristic, then this is a special case of A star where we have no heuristic, so it's optimal. Okay, so we can sort of share these definitions and stuff now. Here's breadth first search. We just use a queue, instead of this priority queue, and here's depth first search where we use a stack. So you can see how little is actually changing in these algorithms here. One last thing before we get to the example, because I'm going to use this in the example, is two small optimizations that we can do to save some additional memory over this algorithm. So yes, this version of the algorithm will work absolutely perfectly. It will produce optimal results if the heuristic is consistent, but let's see if we can add some things that save a little bit of memory. The first thing is the following. So up here, if we look in the algorithm, we're adding children to the open list down here. Then up here in the next iteration, we're going to select one of those children that we added to expand, right? And we say if the state of that node is in the closed list, then don't bother expanding it. But what if we took the additional step of when we generate the child, if it's already in the closed list, then don't even bother adding it to the open list. Because if we add it to the open list, if it is ever selected, it will be immediately discarded, right? So why would we add it in the first place if we know we're going to discard it? So what this can do is it just saves a little bit of memory in the open list, but it doesn't affect the running time of the algorithm whatsoever because we would have discarded it anyway. So this saves memory in the open list, and it basically says if the state of this child is already in the closed list, we know we'll eventually skip it, so just skip it right now. Why not? All right, the second optimization is a little bit more complicated, and I do not recommend actually implementing this for the assignment. Why? Because in practice, it's actually quite slow. So here it is. It says, okay, I've just generated this child. This child has a state and it has a G cost, right? The G cost is how far it's gone so far to get to that node. So if we have a node N that's already in the open list with the same state as this child, and the node's G cost is less than or equal to this child's G cost, then skip adding it to the open list. Why? Because this says if we've already searched a path to this state and it's lower, why would I ever consider going this longer path through this state? Okay, so this is another optimization. However, in practice, depending on the algorithm, the data structures that you're using, the environment, etc., this process of looking through the open list to find this other node that has the same state and comparing their G values, that may actually be really slow. So if that memory saving is not gigantic, which it actually isn't, because it doesn't happen in practice very much, then don't bother using this. But if you can come up with a constant time way of figuring this out, then by all means you can implement this as well. What I'm going to use this for is I'm about to give an illustrated example in slides, and I'm keeping track of the open list. So I'm going to use this just to save space on the slides. So it's a memory optimization because my slide space is so limited. All right. So A star graph search performance. Let's assume that we're using a consistent heuristic. Let C star be the optimal solution path cost. So that's the real answer if we knew it. A star is going to expand all nodes with an f of n less than C star. Every single path that we can possibly go through that is shorter than the optimal path, it is going to go through it. But the cool thing is, it is not going to explore any path that is suboptimal. Or sorry, that's not true. It may explore the start of those paths, but it will not explore any node who has an f of n greater than the true path cost. Therefore, we can say that A star is optimally efficient for h of n. No other optimal algorithm is guaranteed to expand fewer nodes than A star. How do we know that? Because if it did expand fewer nodes, it may have missed an optimal path, right? And any algorithm not expanding, I just said that. So any algorithm that doesn't expand this many may miss it, okay? So being optimally efficient is a pretty crazy good thing to be, right? Not many algorithms that can say that for a given heuristic, this is the best that you can do theoretically. And we know that no algorithm will ever do better than this, right? That's a pretty cool thing to say. So the pros of A star is that it's complete, it's optimal, and it is optimally efficient for a given heuristic. But the cons is that the number of nodes searched can still be exponential in the length of the solution. So when you get to search and you're talking about searching all these different paths, it's pretty hard to get away from the exponentiality of it all. And so for many large problems, A* is much better than uninformed search, but it still may be infeasible in terms of memory, right? If you've got billions or trillions of nodes that you're going to be generating, it's still hard to store all of these things in the open list. And it's the fact that we do need to store these things in the open list, this memory bottleneck, is one of the things that's bad. And toward the end, I'll give a possible hint at a solution to that problem. All right, so now I'm going to go through this step-by-step illustrated example of A* search. And so I've created this little user interface here. On the video, my face is probably covering up the top right part of this. So let me just explain that this says closed up here. So this column is the closed list. It stores states. And these headers along here, I'll explain in a little bit. So we have this environment up here. In this environment, we're going to be able to move in all 8 directions. So cardinal, meaning up, down, left, right, and diagonal. The action costs are going to be 100 for the cardinal actions, up, down, left, and right, and it's going to be 141 for the diagonal actions. Why is it 141? Because a diagonal action is the hypotenuse of a right triangle with 2 sides of 1, so it's the square root of 2, that's the distance. So we're using distance as a cost. And if you take 1.41, you chop off the decimal, you multiply 100. I just wanted to have integers here rather than floating points. So this is it's an approximation, but it's much nicer than dealing with a bunch of floating point decimals because square root of 2 is irrational. So where do we cut it off? We have to cut it off somewhere. So why not cut it off at the 100th? Down here, what I have is an abridged version of the A* search algorithm. While while open is not empty, take a node out, remove the minimum f. If it's the goal, then return the path. If it's states in the closed list, continue. Otherwise, add it to the closed list. Then we do the expansion, and we say, if the states in the closed list, continue. If there's a better path already in the open list, continue. Otherwise, add the child to the open list. And I've color-coded these because we'll see in a second I'm going to use some colors. Okay, so up here I have, I've started up here in the top left. That's my starting node. So I've already added that to the open list. So the open list is going to be the yellow and the closed list is going to be the red as we're continuing with for the rest of the course. And I'm trying to get down here to the bottom right, and hopefully A* is going to find the optimal path to this. And hopefully through this example, you're going to see how A* forms its paths and how there can be suboptimal paths to a given node on the open list, but how we will actually not expand those suboptimal paths. So let's get started. The first thing I do is I have this node over here on the open list. Okay, so what I've done here is I've given sort of a table here with an ID. So these are the nodes. This is the node data structure. The ID, I just have to give it something so we can refer to other nodes. So I'm just giving every node that we generate an increasing integer ID. So the first child we generate will have ID 1, then ID 2, then ID 3, just an integer so I can refer to that. This is the state. So 0, 0 is up in the top left. So this is state 0, 0. The G cost is how far we've come so far. The total cost of all the actions that led us to this node. And of course, for the root node, that's 0 because I haven't taken any actions yet. The heuristic function, that is the diagonal Manhattan distance. So my guess at how far I have left to go is going to be 141 plus 141 plus 141 plus 100. So that if you sum that up, that gets to 523. And so the F cost is just G plus H, which is 0 plus 523, so that's 523. A is the action that led us to this node from the parent node, and the root node has no action, so I've just left it blank. That's just going to be null, essentially. And the root node has no parent, so what I'm going to do right here is I'm just going to write down the ID of the parent. Okay, so that's how we'll get that. So this is the first node. So what we're going to do in our algorithm, the very first step is to remove the node with the minimum F value from the open list. And of course, right now, I only have one node on the open list. So it's pretty easy to tell which one I'm going to remove. So this is the one I'm going to remove, and that's color-coded with this particular line of code down here. So here's the node. This is N0, that's node 0, and its G cost is currently 0. Okay? So what I do, if node.state is the goal, return the path. Okay? I'm not at the goal yet, so I'm not returning a path. If the node's state is in the closed list, continue. Is it in the closed list? No. There's currently nothing in the closed list, so I keep going. I'm going to add the node to the closed list. All right, so that's what I do. I add this node. It is currently on the closed list. So state 0, 0 is on the closed list because the closed list stores states. Now what I'm going to do is I'm going to look at all the possible successors of this node. So all the legal actions that I could do, well, I can't go, I can only have 3 legal actions because there are only 3 states of the environment touching this. So let's go through each of those children. I'm just going to go in clockwise fashion. So the first state, or the first node that I generate, is this one. C means child. And here, the action that generated this one is moving to the right, which has a cost of 100. So the G cost of any child is equal to the G cost of the parent plus the cost of the action, right? So that's going to be 0 plus 100. So the G cost of this one is 100. And now I do these checks. Is this state in the closed list? No, it isn't, because only 0, 0 is in the closed list. Is there a node in the open list already with the same state that has a lesser G cost? No, there isn't. There's nothing in the open list currently. So what I do is I add this to the open list. Okay, so now I've added this one to the open list. So this one gets ID 1 just because it's the second one that I generated. The state of this node is 1 in the X direction, 0 in the Y direction. The G cost is 100. Let's apply the heuristic evaluation, which is diagonal Manhattan. So that's 141 plus 141 plus 100 plus 100. So that's 482. F is equal to G plus H, so that's 582. The action that generated this node was moving to the right, so that's 1 in the X, 0 in the Y. And the parent of this node is node 0, which is this one up here. Okay, let's look at the next child. So this is the next child right here. I'm going to gradually speed up as things go on because I've explained the process, so I won't go through every step of every single expansion. But for the first one, I will. So this child, the action that generated that is down right, which has a cost of 141. So 0 plus 141 is 141. Now I say, okay, is this state in the closed list? No, it isn't. Is this state in the open list? No, it isn't. So add this one to the open list. So now this one is in the open list. And this one, the F cost, well, the G cost is 141. The H cost is 141 plus 141 plus 100. So that's the F cost here. The action that generated was this diagonal down and to the right, and the parent, again, was node 0. So we only have one left to go. So that's this one. Again, this is a down action, so its cost is 100. So it's 0 plus 100, so its G cost is 100. And of course, this state is not in the closed list, and this is nothing in the open list with the same state. So we can just go ahead and add this one to the open list. So after expanding our first node, which is the root node or the starting state, here is our open list. Okay, so our open list has 3 nodes in it because we've generated 3 children, and our closed list has 1 state in it because we have expanded 1 node with a particular state. All right, so now the very first line of our algorithm, since we're done this, we go back to the top. And now we were going to remove the minimum F value from the open list and generate its children. So let's look through the open list. So this one is 582. This one is 523. This one is 523. So we're just going to take the first one as the tiebreaker. So 2 of them have the minimum F value. I'm just going to look at the minimum one. And just as a side note, in your assignment, if you end up with the optimal solution, but the optimal path from A star, but your path is different than my path, typically you can have many, many different optimal paths, but they may be decided based on the ordering of the tie breaking in the open list. So if you had chosen the second one here, you'll still get an optimal path, but your optimal path may be a different path than my optimal path, but they'll have the same eventual cost. Okay. So we've chosen this one. This is node 2, and I've just drawn the parent pointer back to the node that generated it. Okay. So we are expanding this one, and now we have to look at all the children of this one. And this one has far more children than the first one. So here we look back up. I'm going to start on the top left and go clockwise again. So this one, its G cost is going to be 141 plus 141, because we went diagonally and then diagonally again. But we're going to stop looking at this one because the first check, this one is already in the closed list. So the node here representing state 0, 0, we look over here, state 0, 0 is already in the closed list, so we can skip this. We don't need to add this node back to the open list. Why? Because this node will never be re-expanded, because how can an optimal path have a revisit to a state in it, right? So we skip that one. Now we're going to look at this one. So this is already in the open list, but that's fine for now, okay? So here we've gone down right to get to this parent node. The G cost of that was 141. So this node is going to have G cost 241. Why? Because to get to the node that in the search tree, we would have had to go down to the right and then up. So that's 241. So now we can say, okay, is that state in the closed list? No, right? This state is not in the closed list, so we keep going. Is there a node in the open list with the same state but a lesser G cost? Okay, let's have a look at that. So if I look through, the state of this node is what? 1, 0, right? So I look through my open list and I see, oh wow, okay, so there is a state, there's a node in the open list with the same state. Let's have a look at its G cost. It's 100. So the path in the open list to this node costs 100. The path that I'm currently considering costs 241. So obviously, if we're going to the same node with a worse path, that's a tongue twister, then we don't really care about this one. Now, I could just add it to the open list. That's fine. But it would never be popped off the open list because its F cost is just going to be worse than the F cost of the other one, right? But because I'm trying to save space here, I have colored this green because there is a better path to that node, to that state already in the open list. So let's not add that to the open list. Okay, see how that optimization works? It's only a memory optimization because it would never actually have been popped off the open list because a better path exists. So we're just going to skip that. We're not going to add it to the open list, but that's an expensive check, right? So that may actually slow down your algorithm because it doesn't affect the running time, it just affects the memory. All right, next child, up and to the right. All right, is this one. So this is 141 plus 141, so that's 282. Is this one in the closed list? No. Is it in the open list? No. So we add that one to the open list. The next one, well, we can't go here because this is a wall. We can't go into the walls. We can't go there. Here, this is a wall, so the next one will be right here. So we look at this one. So this is 141 plus 100, so that's 241. It's not in the open list and it's not in the closed list, so both of those checks fail, so we add it to the open list. Now let's go to this one. So this one is 141 plus 141, so this is 282, right? So this one is not in the closed list and it's not in the open list, so we add that one to the open list. Now, we keep checking. This is the last one that we'll check. We say, okay, 141 plus 100, so the G cost of this one is 241, but state 01 already exists in a node on the open list, and its G cost is 100, so we skip adding this one to the open list, okay? And again, just to drive it home, I don't recommend implementing this one for your assignment because I think in practice it's usually too slow to matter. So we don't add that one to the open list, and after our second expansion, here is the state of our open list. Okay, now I'm going to speed up a little bit because you got the idea of how this works. So now what do? We look for the minimum F value. This one happens to have the minimum F value. In fact, there are two that are tied. We're just going to take the first one. So we're going to check its children. So this one, obviously, this one is in the closed list, so we don't take that one. This one is a worse path than we already have to that node, so we skip adding that one. That's the green check below. This one, that one's already in the closed list, so we know we skip that one. This one down here, however, this one is G cost of 241. It is 1, 2. I have a 1, 2 of 241. So I already have a path of equal quality on the open list. So why I don't need this one, so I can skip adding that. But here is something interesting. This is the first time this has happened. Now I'm considering this path, which is 100 plus 100, so it's down, down. But look at this. If I look at the open list, I have, so this is state 0, 2. So a node with state 0, 2, this G cost is worse than this one, okay? So normally what you would do is you just add this one to the open list, right? And then this node will be expanded before the other one because its F cost will be less. So you'll never actually pick that worst path from the open list. So we don't have to worry about it. But just for the case of the slides, because I'm going to run out of room, here is an optimization that you could potentially do that is very tricky to implement in practice. But if you have a node in the open list with the same state on a worse path, you can remove it from the open list if it is computationally feasible to do so. Okay? It will not affect the running time of the algorithm. It will just be a slight memory savings. And that's what I'm going to do here, is I'm going to take these two and only keep the best one. All right, so that's why I did that there, just to save memory on the slides, because slide memory is very limited. Okay, so now we've expanded that node. So here is the state after 3 expansions. Let's keep going. Let's pick the minimum F on the open list. It is this one right here. So you can see that it's, you know, as humans, we can see, okay, this isn't on the optimal path, but it thinks it's going, right? Because the heuristic is guiding us in that direction. Okay, so let's have a look at this one. Let's look at the children. Well, obviously, I'm skipping things here, so I'm not going to consider things that are already on the closed list or all of these things that are all blocked. So the only child we're going to consider is this one, but that one is already on the open list with a lesser G value, so we don't bother adding this one to the open list. Okay, next, which one has the minimum F? Well, let's just take this top one. Here we are. Let's look at its children. Here's a child. This is the same case that we just had, right? This state, 2, 0, exists on the open list with a worse G value. So I'm going to delete that one from the open list and add this one instead. And don't do that on the assignment. Again, just doing it on the slides, okay? And then I've got nothing else to consider because they're all either on the closed list or they're blocked. Next, okay, next node. Down here, this one is 582. So I'll take that one. All of its neighbors are on the closed list, so I skip it. So now I've only got one left. Choose this one. Generate its children. Neither of those are on the closed list, so we add them to the open list. Now I pick this one, which has the minimum F value, and so on and so forth. This one is already there with a better path, so we don't consider it. Now I'm just going down. So from here on, we're just going down toward the goal. But here is a key, okay? Key part. When I select this node and I generate a child, that is the goal. It is not at the point of child generation that I think that I've reached the goal. I don't say I have found the goal here. I am not checking for the goal in the expansion. Why? Remember up here in the top left? The first time I got to this node up here as a child, it was on a terrible path, right? So it's not at the point of child generation that we say I found the path. It's at the point where I select the minimum F value from the open list when I found the path. Because only at that time am I sure I'm selecting it. So I add the node, which happens to contain the goal, to the open list. All right, then I generate the other child. And now, when I select this node from the open list, and it happens to be the goal, okay, now I'm sure I have found the optimal path, okay? And then I just follow the parent pointers from this back to the start, and that's the optimal path. So that's the A-star algorithm. So you can see now that yes, there can be nodes on the open list that are not on optimal paths, but you won't select them because the other ones with better F costs will be selected first. And it will select all of them. Even the ones down here, every single node with an F cost less than the optimal path will be selected, but nothing with an F cost greater than the optimal path will be selected. Okay, let's take a look at A star and let's modify it a little bit. Yes, question?
If there were, on the last slide, if there were no obstacles, then you would have sort of taken the diagonal and then down.
Depending on tiebreakers.
Sure.
Yeah. So I'll show that when we introduce assignment 2, how tie breaking can dramatically impact the number of nodes. So the direction that you expand in is based on tie breaking. Okay. So weighted A star. We can tweak the performance of A star by adding a parameter or a weight called W. So when we multiply, and then what we do is we take this W and we modify the algorithm by multiplying the heuristic by W. So now f of n is equal to g of n plus W times h of n. So if this weight is really high, we are really trusting the heuristic, and if it's really low, we are not trusting the heuristic. As we set the weight greater than 1, A star favors going in the direction of the heuristic more and more. If the weight is less than 1, A star trusts the heuristic less and less. So what happens as W approaches 0 or infinity? This is a great exam question. So for A star, f of n is equal to g of n plus h of n, right? For UCS, f of n is equal to g of n plus 0, essentially. It's only g of n, so it's 0. For greedy best first search, f of n is equal to 0 plus h of n. And for weighted A star, f of n is equal to g of n plus h of n times some weight. So what weighted A star does is it gives us this sort of knob that we can tune, where if the weight is 0, then we approach the same behavior as uniform cost search. And if the weight goes up to infinity, then all we care about is the heuristic, and so we turn A star into greedy best first search. And what effects do those have? Well, I'll show you now in a second when I go to this search demo. So on my website here, I have this version of the assignment, which is, it's like the assignment, but it has some more options here. So let's just have a look at, this is the A star search algorithm. So you can see that in comparison to breadth first search, it expands far fewer nodes than breadth first search. The reason breadth first search is wonky here is because when the action costs aren't the same, it's no longer optimal, right? And so we have action diagonals, etc., which aren't the same. Let's look at uniform cost search. Uniform cost search, let me go to this one. So uniform cost search, if I animate it, what it does is it always takes the next closest thing, which essentially just expands out in a circle, right? So if we're taking G minimum G means the closest thing to the start. So it's literally expanding out in this circle because it's taking the next thing. All right, there we go. We finally reach it, and we know that's the goal. So that's uniform cost search. Here is greedy best first search. It goes straight to the goal because there are no obstacles, right? So just keep that in mind. Now let's go to sparse caves. I think this is a good example. Let me turn off this grid, and I will use uniform cost search to go from here down to here. So uniform cost search is just expanding out in that circle, right? It's almost like a mold growing. It's almost like literally exactly like if you look at a petri dish of mold, it's a breadth first search. And so you can see, okay, that's a lot. It's not taking any information into account, right? But it will eventually find the goal, but kind of once it has searched absolutely everything. Okay, now let's run A star search, right? A star search, actually let's run greedy best first search first. So this is greedy,
It went almost straight to the goal. Let's look at that not so fast. It's going where it thinks is the right direction, but then it sort of has to fill up all of these caves that are incorrect, right? But then it does finally reach the goal. But you can see here that this is not the optimal path cost, because the path goes out to the right and then it comes back in, and so that's the way it searched. So it was far fewer nodes expanded, right? And the search took way less time, but it's no longer optimal. So let's look now at A star. A star is kind of in between those two, where it goes in the direction of the goal, ideally, but it also has to consider how far have I gone so far. So this is what it's doing. The bane of any search algorithm are these sort of concave structures. Okay, so we eventually get there. Okay, so we eventually get there. This is the optimal path because we know A star is optimal. But let's have a look at this. Okay, instant path. This is A star. This is uniform cost search. So it's definitely fewer nodes than uniform cost search. The closed list size 9968. The path costs 16,457. So let's look back at A star. A star, same path cost because both algorithms are optimal, but far fewer nodes generated. Now, let's look at greedy best first search. 19,000 path cost. So it's way worse. It's no longer optimal, but we searched a fraction of those nodes, right? So what we can do, let's say we have a video game, right? We have weighted A star. So weighted A star with a W of 0 is equivalent to A star, right? So as we start bumping this heuristic up, what we're going to see is the more that we value the heuristic, typically the fewer nodes are going to be searched, but the less optimal the solution is going to be. So let's take 1 and move it to 1.1. Okay, that actually kept an optimal path, right? And there's a property is that if you take a weight of W, then you can guarantee that you're going to be suboptimal by at most a factor of W. So if W is 2, you know that you're going to be at most double the optimal path, okay? But here we happen to stay optimal. Let's bump that up to 1.5. Okay, now we're no longer optimal, right? We'll keep bumping it up. Let's go to 2. Let's go to 4. Let's go to 8. And then if we finally go to greedy best first search, where it would essentially be infinity, then we get something like that. So this is how all these algorithms are related. This weighted A star can approximate these different algorithms. But sometimes, let me just show you a maze. So this is a maze structure here. Sometimes, let's say we have greedy best first search, and we want to go from here to here. Right? This doesn't always work out best for us. All these heuristics and stuff typically don't really help us in these really complex mazes, because the closer the heuristic is to the best possible path, the better it will help you. And in these mazes, it's going to be really, really far off from that. So if I go here now and I say, I don't have much time left. If I were to say, all right, this is now 66,206, and if I turn this into A star, and let's just go the instant path, it's 55,000, right? So in this case, if I toggle back and forth between greedy best first search, it didn't help us a ton in terms of the number of nodes expanded, and it really pooped the bed in terms of the optimal path. So you really only want to be trusting the heuristic if there aren't many obstacles. And the more obstacles that you put into your environment, the less and less that heuristic is going to end up helping you.